Hey folks, Tony here. The topic for today's walkthrough is the reverse engineering of device firmware, and our target is going to be this little guy. It's D-Link's 932L webcam. It retails around 30 bucks, and it's a great entry point when you're first learning about reversing firmware and hardware. As a matter of fact, in a later project, we're going to crack the case on this thing and go the hardware route, but let's stick with the firmware for now. Here's how it's going to go. We'll start by downloading the firmware from D-Link support site, because you gotta love it whenever they make things that easy for you. Then we're going to slice and dice the binary with some simple tools and methods, and the goal of all that's going to be to extract the file system, right? So that we can leave you in a place where you can browse the contents of the file system, just explore, like you would if it were on any other computer. And we're doing all this because getting to this state where we can browse the file system is kind of the first step when you're reverse engineering. Remember, attackers reverse engineer firmware so they can find vulnerabilities, right? Things they can exploit to attack other elements of the ecosystem. The backdoor vulnerability I blogged about last week, that's a pretty good example of what we're talking about here. Now, we're going to do all of our work today from a Kali VM. Kali is a Linux distribution that ships with a suite of pen testing tools. It's free, and it comes with everything we're going to be using today. If you want to try any of this stuff on your own, I strongly recommend grabbing a copy and running it. There's actually a link to it in the blog post below. So let's switch over to that now. Okay, here we are on the Kali VM. I've got the D-Link support site pulled up. We can see our camera on the right there. I have version A of the hardware for this thing, so it looks like the latest firmware for me is version 1.14.04. Let's download that firmware and switch over to the terminal so we can see what we are working with here. Zip archive, so let's unzip it. Okay, it looks like I've got two files, a PDF with the release notes, and then below it a .bin, so a binary file. That's probably what we're after. We can double check that by running file against it. The file command is just a way of asking Linux what it thinks about the contents of this file. And it says, yeah, I think it's data. That's to be expected. Now, if you're used to working with text files that you can just like pop open and read like this, yeah, you're going to have kind of a bad time, right? It all looks like junk. And that's because this file isn't meant for human eyes. It's meant to be interpreted by a machine, by the camera. And this is where the reverse engineering really starts. We're going to take this file that we can't read, work it over, and wind up with a file system that we can browse through. One of the first things we can try as we're doing that is to search the file for printable characters, right? Things that we actually can read. The strings command will do that for us. So we're going to feed strings this binary and ask it to tell us if it sees 10 or more printable characters in a row. And just to keep everything clean for us, we don't want to get overwhelmed, just show us the first 10 times that happens. Okay, that's way better. Now we can read this stuff. And then check that out. The first line there says U-boot. That's great. That's going to be handy later. We can also see a bunch of other stuff in here too. And Strings is a great tool. You can use it to find API keys and other fun things in files, but it's not high fidelity. We're only looking at the printable characters here, so we're going to lose a lot of the meat of what's in the file. It can also be hard to orient ourselves in this when we're just looking at output, like if it's in this format. So let's use a different tool. Let's try something called binwalk. Okay, binwalk, when we feed it a binary file, just like strings, it's going to parse it out, but it has a library of signatures in it, things that it looks for in a file. And when it comes across something it recognizes, it notes the location of it in the file, basically just reverse engineering to create a table of contents for us. So let's go ahead and run binwalk against that now and see what we get. That was easy. Looks like we can see it's called about 10 places in the file where it recognizes something. And cool, hey, the first one there is uboot 113, the thing we saw in the strings output. And it says we can find that, the location of the file is 106352. Now, I'm happy to see that uboot's in here because that means that it's running Universal Bootloader. When you first power on a device, the bootloader is what tells the machine, hey man, here's the operating system you're going to be running today. So that means uboot inherently has to know where the OS is. And the way it knows that is by tracking it with a uimage file. And sure enough, if we look down below past that HTML stuff, there it is. It's the uimage header. The formatting is ugly here, but I do see some pretty cool stuff. I see the image type is OS kernel image. Compression type is Lisma. That just means it's been compressed into a Lisma archive. It's basically the same as a zip file, just like you're used to, just a slightly different format. And then finally, the image name is Linux kernel image. So that's all super promising, especially because right after that header, what is that, starting at 327744, there's a big old hunk of Lisma compressed data in there. It's great to know this is there, right? But it doesn't really do us a whole lot of good if it's just wrapped up and stuck in this binary. We need to carve it out so we can work on it. Binwalk has the ability to do some of that carving for us, but just to give you some exposure to some other tools, we're going to use something called DD. And DD stands for data duplicator, right? Just like you copy files on a computer, except DD will copy portions of files off of something. So we're going to say, DD, I'm going to give you as an input file this binary. I want you to go ahead and skip ahead for me to 327744 because that's where the Lisma starts. So it's going to copy everything beyond that point. Use a block size of 1. Don't worry about what block sizes are for now. You can Google DD block size if you want to learn more about it later. And when you copy all this stuff, you got to write it somewhere. So write it to an output file, and let's call that kernel.lisma. Okay, give it a second to do its thing. And as soon as it's done, we are going to try to extract this Lisma archive. We can double check to make sure that it actually worked the way we wanted to by running file against it, just like we did earlier. So file kernel Lisma. And cool, it recognizes that this is a Lisma compressed archive. So that means that we can unlisma it, right? Just like we unzip, so unlisma kernel. Okay. And let's file the results. More data, just like we had when we first started, right? And just like we did at the beginning, we could run strings against this, but since you've already seen that, let's crank binwalk on again. Binwalk kernel, so that we can build out that table of contents. Whoa, way more stuff in here than there was last time, right? And check it out, down at the bottom here, there's even some Lisma compressed data. It starts at what, 4038656. We're going to come back to that in a second. For now, let's scroll back up to the top just to get a lay of the land. See what we're working with here. Lots of Unix file paths. That's what you'd expect, given we're in a Linux kernel. And okay, finally, cool. Linux kernel version 2.6.21. That's a really good piece of information just on its own. Linux is up on version 4 now, and Linux 3 came out in like 2011, I think. So even though this firmware is relatively new, it just came out a couple months ago, the kernel it's built on is significantly older. So try Googling Linux 2.6.21 vulnerabilities to see why that's relevant and can be fun. But for now, let's just cruise back down to that Lisma file. Now, the last time we did this, there was a nice uimage header, right, that explained everything that was in that Lisma, and we don't have that benefit this time, but it's really not that big of a deal because the process is exactly the same. We're going to use dd again, and just like we did last time, we're going to say dd, I've got an input file for you. This time it's the kernel file. I want you to skip ahead to where this Lisma archive starts, which is 4038656. Keep the block size at 1. And create an output file for me. We don't know what it is, so let's call it mystery.lisma and let it do its thing. Okay, cool, that's done. We're going to live dangerously this time. We're not going to run file and everything else against it, because the worst that can happen is we get an error message. So let's just unlisma it and run file against the results. Cool, we got a CPIO archive. That's really good news because a lot of manufacturers, D-Link included, will store the file system in a CPIO archive. So all we have to do now is unpack this and we should be all good. It will be a whole file system though, right? So it's going to be pretty big. So let's go ahead and make a directory to keep things tidy. We're going to call that directory CPIO, and let's go ahead and change directory into CPIO now. Okay. And I'm going to say, hey, CPIO, I want you to unpack this archive. I want you to create directories whenever you need to. I don't want you to monkey around with the timestamps on it, maintain those as they are, just because it might be useful for us later as we're digging through stuff. Also, I'm going to be unpacking a Linux file system onto a Linux machine, and I don't want this to go and overwrite any of my system files on my workstation here. So I'm going to say, by the way, CPIO, no absolute file names, just to make sure that we keep everything nice and clean. And then finally, we got to tell it, I want you to run this all against this mystery file that we have here. Okay, that looks like it did its thing. Let's take a look. And yeah, it did, it worked. Cool, we have everything. The whole file system is unpacked here. We can kind of browse through it now to our heart's content. We can do all sorts of stuff. Let's take a look at, what is that, etc RO. This thing's got a web interface on it, right? So we can look for web application vulnerabilities from the inside out. I see a bunch of web stuff written up here, right? So let's see, web. Cool, so we can dig in there to look for that. We can also take a look at things like system commands, right? By looking in places like sbin. Wow, there's tons of stuff to look at in here. Some of this stuff is scripts, the stuff that's ending in .sh, right? Those are human readable. So we can pop those right open. Let's take a look. We can more sbin config.sh, right? Lots to look at in here. What else? We've got, let's try, storage. See what it's got. Cool, it looks like it's actually setting up how some accounts are created. What else? I can see some stuff for FTP. Kind of the list just kind of goes on and on here in terms of what you can do. Taking this back to last week's backdoor vulnerability, the Spider Labs team got into the firmware just like we did here, and then took a look at bin login, right? And they reversed that binary, and that's where they found the references to DBL admin, and that's where the backdoor lived. Anyway, short on time, so let's wrap this whole thing up by looking at what we did here today. We did everything today on a Kali Linux virtual machine, and from that VM, we went to D-Link's website, where we downloaded the firmware for this camera, the D-Link 932L. The first thing we did was try to read the firmware like it was a text file, and that was pretty ugly. So we used a few tools to dig into it. We ran strings against the binary, so we could check out the printable characters in the file. We saw some stuff, but we wanted to be a bit more organized, so we ran binwalk against it, which parsed the whole thing out and created a table of contents for us. We then saw the U-boot loader, and since that's responsible for loading up the operating system, we knew we were on the right track. When we saw a Lisma compressed archive that looked like it might have what we wanted, we went ahead and used DD to carve that out. The result was a Lisma archive. We used file to make sure that that Lisma archive was in good shape, and then we unlismed it to extract the archive. We ran file against the result, and again, saw it was a data file. So we ran binwalk against it, and saw that the Linux kernel was pretty old, and also saw some more Lisma in there. So another trip back to DD to carve out the archive, and another round of unlisming, and we had a CPIO archive. We talked about how manufacturers will pack their file systems into CPIO archives, and sure enough, when we made a directory and unpacked it in there, we had access to the file system. And that was our goal, to leave you in a state where you could browse the file system to snoop and explore things on your own. Now, if you're interested in trying this out, you'll find a step-by-step guide below in the blog. Hopefully, this gave you a bit more understanding of how reverse engineering works and what role it can play in IoT security. That's it for now. Thanks for watching.